Dear students, welcome back to the lecture series on solid state. In this session, we will have a discussion on structural transitions in polymorphic forms of titanium dioxide. Before moving on to today's session, let's discuss the assignment questions of the previous class. Let's begin with the first question. Electron diffraction experiments confirm option A, the particle nature of electrons, option B, the wave nature of electrons, option C, the dual nature of light only, and option D, the charge to mass ratio of electrons. In the previous class, we discussed about electron and neutron diffractions, and both these methods rely on the wave particle duality. So, the electron diffraction experiments are a direct proof of the wave nature of electrons. So, the correct option is option B, the wave nature of electrons. Question number 2. Low energy electron diffraction or LEED is primarily used for option A, determining bulk crystal structure, option B, investigating the surface structure of crystals, option C, analyzing amorphous materials, option D, measuring magnetic moments. Low energy electron diffraction is an electron diffraction method which is primarily used for investigating the surface structure of crystals. Electron diffraction methods. In electron diffraction methods, electrons are scattered and these electrons cannot penetrate deeply into the crystal planes. They can penetrate only up to first few layers or first top layers. So, the electron diffraction methods are generally employed for studying the surface structure of crystals. So, here low energy electron diffraction, which is an electron diffraction method, is generally used for investigating the surface structure of crystals. Let us move on to the next question. Which diffraction technique is most suitable for monitoring thin film growth in real time? Option A, X-ray diffraction, option B, TED, that is transmission electron diffraction, option C, RHEED, reflection high energy electron diffraction, option D, LEED, that is low energy electron diffraction. We have discussed about two types of electron diffraction methods, LEED and RHEED, and reflection high energy electron diffraction, which employs high energy electrons, are generally used for monitoring the thin film growth in real time. So, the correct option is option C, RHEED. Fourth question. Neutron diffraction differs from X-ray diffraction because option A, neutrons interact with electron clouds, option B, neutrons interact with atomic nuclei, option C, neutrons are charged particles, option D, neutrons have no wavelength. We know that neutrons are neutral particles and they possess a magnetic moment, and in neutron diffraction, neutrons interact with the atomic nuclei. They penetrate deeply into the atomic nuclei. So, in question number 4, neutron diffraction, how it differs from X-ray diffraction? X-rays interact with the electron clouds or electrons, and whereas in neutron diffraction, neutrons interact with the atomic nuclei. So, the correct answer is option B, neutrons interact with atomic nuclei. Let's move on to the fifth question. Neutron diffraction is most useful for locating option A, heavy metal atoms, option B, electron densities, option C, light atoms like hydrogen, and option D, crystal vacancies. We have seen that since neutrons can penetrate deeply into the atomic nuclei, they can be used for identifying light atoms like hydrogen. So, the correct option is option C, light atoms like hydrogen. Last question. The magnetic structure of crystals can be best studied using option A, X-ray diffraction, option B, electron diffraction, option C, neutron diffraction, and option D, infrared spectroscopy. So, among the three diffraction methods we discussed so far, X-ray diffraction, electron diffraction and neutron diffraction. Neutron diffraction helps in the study of magnetic structure of crystals. So, the correct option is option C, neutron diffraction. Now, let us move on to today's topic, structural transitions in polymorphic forms of titanium dioxide. By the end of this session, you will be able to define what is polymorphism and identify the polymorphs of titanium dioxide. To describe the crystal structures of rutile, anatase and bruchite. To explain thermal and pressure induced transitions. To understand how size, temperature and other impurities affect the stability of different polymorphs. Recognize applications related to different phases. So, before discussing about the structural transitions, let us see what is meant by polymorphism. Polymorphism can be defined as the existence of a material in more than one crystal form with the same composition. Okay. That is, a crystalline solid can exist in different structures, crystalline structures or crystalline forms with the same chemical composition. Such crystalline forms are called polymorphs. Okay. So, each crystalline structure with the same chemical composition are called polymorphs and the phenomenon is called polymorphism. Each form, that is each polymorph, differs in crystal symmetry and atomic arrangement. That is, they differ in the crystal symmetry as well as the arrangement of the structural units. Different polymorphs of a compound will have different physical properties also. So, polymorphism is the existence of a crystalline material in more than one crystal form with the same chemical composition. So, such crystal structures are referred to as polymorphs and the phenomenon is called polymorphism. Each polymorph differ in their crystal symmetry as well as the arrangement of atoms or arrangement of their structural units. And different polymorphs of a compound may have different physical properties. A very good example of polymorphism can be seen in titanium dioxide, TiO2. Titanium dioxide has three important polymorphs, namely rutile, anatase and bruchite. There are also some other less common high pressure forms like TiO2-2, which is represented like this, TiO2-2, TiO2B and cubic TiO2. Okay. These are some less common forms, but now we will concentrate more on the three important polymorphic forms, namely rutile, anatase and bruchite. As you can see in the figure, these three polymorphs, that is rutile, bruchite and anatase, differ in their crystalline structures, okay, or the arrangement of the structural units. So, all three forms of TiO2, that is all three polymorphs of titanium dioxide, namely rutile, anatase and bruchite, are made up of TiO6 octahedra That means each titanium atom is surrounded by 6 oxygen atoms. Then where lies the difference? The difference between the polymorphs lies in how these TiO6 octahedra are connected. That is, whether they are connected by edges or by corners. Okay. So, when we deal with the structures of the titanium dioxide polymorphs, whether it is rutile, anatase or bruchite, all the 3 polymorphs are made up of TiO6 octahedra, or each titanium atom will be surrounded by 6 oxygen atoms octahedrally. But the difference lies in the fact that how these TiO6 octahedra are connected, whether they are edge sharing or corner sharing. Now let us discuss the crystal structures of each polymorph. First let us see the rutile phase. Among the 3 polymorphs of titanium dioxide, rutile is the most stable form at room temperature. It is characterized by a tetragonal structure, as you can see in the figure. And in the tetragonal structure, each Ti4 plus ion is surrounded octahedrally by 6 oxide ions. As you can see here, the blue sphere represents the titanium ion Ti4 plus ion, and you can see that it is surrounded octahedrally by 6 oxide ions represented by the red spheres. Okay. And each oxide ion is surrounded by 3 Ti4 plus ions. When we say each Ti4 plus ion is surrounded octahedrally, it is not a perfect octahedron, but it is actually a distorted octahedral manner. Okay. And that is what the symmetry allows. So, each Ti4 plus ion is surrounded in a distorted octahedral manner by 6 oxide ions, and each oxide ion is surrounded by 3 Ti4 plus ions. The TiO6 octahedra shares both edges and corners, thereby giving rise to a tightly packed arrangement. And rutile is the densest and most thermodynamically stable phase. Okay. So, among the 3 polymorphs of titanium dioxide, rutile is the most stable form at room temperature. It is characterized by a tetragonal structure, as you can see in this figure, and in the tetragonal structure, each Ti4 plus ion is surrounded distorted octahedrally by 6 oxide ions, and each oxide ion is surrounded by 3 Ti4 plus ions. The TiO6 octahedra shares edges as well as corners, thereby giving rise to a tightly packed arrangement. So, this is the densest and also the thermodynamically most stable phase of titanium dioxide. So, next we will see another polymorph, anatase. Anatase is also characterized by a tetragonal structure, but it has a more open structure, as you can see in this figure. Here the octahedra share 4 edges and 4 corners, leading to lower density and a slightly distorted octahedral geometry. So, anatase also has a tetragonal structure similar to rutile, but here the structure is like a more open one. So, here the octahedra share 4 edges and 4 corners. So, that leads to lower density and a slightly distorted octahedral geometry. And because of this more open structure and lower density, anatase is metastable. That is, their stability is less compared to that of a rutile phase. And it is stable only under certain conditions. That is, under certain conditions of temperature and pressure, anatase phase is stable. But it always have a tendency to convert to the rutile phase over time or on heating. So, when we apply any minute changes to conditions like temperature or pressure, the anatase phase have a great tendency to convert it into the rutile phase, and that is why we say anatase is metastable. Okay. So, anatase with a tetragonal structure similar to that of rutile, but it has a more open structure leading to lower density and a slightly distorted octahedral geometry. And another characteristic feature of anatase is that it is metastable. That means it is stable only under specific conditions of temperature and pressure. Any minute changes occurring will convert anatase into rutile phase. And the third polymorph of titanium dioxide is bruchite. Different from the rutile and anatase, bruchite crystallizes in orthorhombic structure, as you can see in this figure. And orthorhombic crystal structure, we know that it is less symmetric. So, the bruchite is less symmetric as well as it is also metastable. It is not as commonly found, but it has an interesting mix of edge and corner sharing octahedra. And among the three phases or three polymorphs of titanium dioxide, bruchite is the least stable phase. So, bruchite crystallizes in a orthorhombic structure. It is less symmetric, it is metastable. That means bruchite will also have a tendency to convert it into a more stable form, say rutile, under specific conditions of temperature and pressure. So, we have discussed the crystal structures of three polymorphs of titanium dioxide. Now, let us see how structural transitions occur among the three polymorphs of TiO2. A significant structural transition occurring in TiO2 is the anatase to rutile transition. So, when we heat anatase, typically between 600 to 1000 degree Celsius, in the range 600 to 1000 degree Celsius, the anatase form gradually transforms into the rutile form. And this structural transition is also called a reconstructive phase transition. Now, what is a reconstructive phase transition? That means the bonds will break and reform as the TiO6 octahedra rearrange into a denser structure. We have seen that both crystallizes in tetragonal structure, that is both anatase and rutile crystallizes in tetragonal structure, but rutile has a more dense form or more tightly packed arrangement, whereas anatase has a more open structure. So, during the transition from anatase to rutile, upon heating between 600 to 1000 degree Celsius, there will be breaking of bonds and reforming, and the TiO6 octahedra rearrange themselves into a more denser form, and that is called a reconstructive phase transition. Now, why such transition occur? It is because rutile has lower Gibbs free energy. So, when we speak in terms of thermodynamics, we know that lower the energy, greater will be the stability. So, when the Gibbs free energy decreases, stability increases. So, among the three polymorphs of titanium dioxide, the rutile form has lower Gibbs free energy at high temperatures, or in other words we may say it is the more thermodynamically stable state. On the other hand, anatase form has higher Gibbs free energy. So, a system will always have a tendency to move from high energy to lower energy in order to attain stability. So, that is why anatase have a tendency to get converted into rutile phase. Why? Because rutile has a lower Gibbs free energy at higher temperature. Lower Gibbs free energy means greater is the stability. Now, what all factors does this structural transition depend on? The main factor is the particle size. Smaller anatase nanoparticles are more stable and they need higher temperature to convert. So, if the particle size is less, they will be quite stable. So, you need more temperature or higher temperature to convert it into another polymorph. Next is the impurities or dopants. When we add certain elements like silicon, aluminum, iron, etc., they can delay or prevent the structural transition. Another factor is the atmosphere, that is the oxygen content or the air content or pressure can affect the rate of transformation. So, this anatase to rutile transformation is a very good example of how both thermodynamics and kinetics control a structural transition. So, here we have discussed a few factors affecting the structural transition. So, the particle size is one factor. When the particle size is less, they will be quite stable. For example, when we consider anatase to rutile transition, smaller anatase nanoparticles are more stable and they need higher temperature to convert. Similarly, the presence of dopants or impurities may delay or prevent the structural transition. The atmosphere, that is the oxygen content, air or the pressure can also affect the rate of transformation. Another transition, structural transition occurring in TiO2 is the bruchite to rutile transition. So, bruchite also transforms into rutile on heating, usually in the 700 to 800 degrees Celsius range. We have seen that like anatase, bruchite is also metastable, that means it can easily get converted into the rutile form. So, it moves towards the more stable rutile phase as temperature increases. And bruchite is very less commonly found, and so this transition is not as widely studied as the anatase to rutile transition. Okay. So, bruchite is a metastable one, which is an orthorhombic structure. So, that also has a tendency to get converted into rutile phase upon heating, usually in the range 700 to 800 degrees Celsius. Now, next is some high pressure structural transitions. At high pressures, titanium dioxide undergoes several other structural transitions because atoms are forced closer together and titanium's coordination number can increase from 6 to 7 or 8. For example, one transition is TiO2, which is an orthorhombic type, which is of the similar to lead dioxide type. So, it is at a very high pressure of 2 to 6 gigapascals. Similarly, TiO2B form, which is a monoclinic, and it is often found under hydrothermal or low temperature conditions. Next is cotunite type TiO2. It is at very high pressures above 60 gigapascals and has extremely high density. So, these high pressure forms, they usually revert back to rutile when the pressure is released. Several thermodynamic and kinetic factors affect the structural transitions in TiO2. So, in terms of free energy, we know that rutile has the lowest Gibbs free energy. So, thermodynamically, rutile is the most stable at all temperature and pressure. When we look at the kinetic aspects, anatase and bruchite persist due to high activation energy. So, kinetically stable is anatase as well as bruchite. When we consider the particle size at nanoscale, the surface energy stabilizes anatase, that is smaller nanoparticles below 14 nanometers. So that's why many photocatalytic TiO2 materials are prepared as anatase nanoparticles. Why? Because they are more stable than the rutile phase when their size is smaller. So they stay in that form even though rutile is normally the stable one. So thermodynamically the most stable form is the rutile form, but when particle size is decreased, for example below 14 nanometers, the surface energy stabilizes the anatase phase. So when we synthesize photocatalytic TiO2 materials, they are usually synthesized in the anatase phase because they form stable structures. By what all methods we can identify or distinguish the polymorphic forms of TiO2? We have the X-ray diffraction methods which can detect the crystal structure changes, differential scanning calorimetry or DSC to detect heat changes during the transition. We can use Raman spectroscopy that identifies the phase specific vibrations, or transmission electron microscopy TEM to directly visualize the particle morphology and reveals mixed phases. So these methods help us to identify and distinguish the rutile, bruchite and anatase forms in TiO2. Now let us see the applications of the three polymorphs of TiO2. Anatase, as we said earlier, is excellent for photocatalysis. It is a very good photocatalyst. Can also be used in solar cells, self-cleaning surfaces due to its high surface area and band gap of 3.2 electron volt. On the other hand, rutile is generally used as a white pigment in paints, plastics and cosmetics because of its high refractive index and opacity. Bruchite has intermediate properties and it is sometimes used in composite catalyst, in the preparation of composite materials and as catalyst in composite materials. So these are the general applications of the three polymorphic forms of TiO2. So in this session, we have discussed about the structural transitions in the polymorphic forms of TiO2. So we have seen that TiO2 exists mainly as rutile, anatase and bruchite polymorphs. All the three forms has TiO6 octahedra but differ in the way in which they are linked or connected, that is whether they are edge shared or corner shared. Rutile is the most stable one, whereas anatase and bruchite are metastable. Then we have seen the structural transitions, the transitions from anatase to rutile and bruchite to rutile. Under high pressure conditions, new dense forms appear. The phase transitions are governed by several factors like temperature, pressure, particle size and the presence of impurities. So these structural transitions are key for applications in photocatalysis, in the synthesis of pigments and energy materials. Now let us discuss a few questions based on today's topic. First question, which of the following polymorphs of TiO2 is thermodynamically most stable at room temperature? Option A, anatase. Option B, bruchite. Option C, rutile. Option D, TiO2 2. We have seen that among the three polymorphs of TiO2, that is anatase, bruchite and rutile, rutile is thermodynamically the most stable one. So the correct option is option C, rutile. Now let us move on to the second question. The coordination number of titanium in all major TiO2 polymorphs, that is rutile, anatase and bruchite is option A 4, option B 5, option C 6 and option D 8. we have seen that in all the three polymers of TiO2, each Ti4 plus ions is surrounded by 6 oxide ions. So, when each titanium is surrounded by 6 oxide ions, then that means the coordination number of titanium is 6. So, the correct option is option C, 6. Now, let us move on to the third question. The brookite to rutile transition occurs approximately at option A 200 degrees Celsius, option B 500 degrees Celsius, option C 700 to 800 degrees Celsius, option D 1000 degrees Celsius. So, brookite phase is a metastable one and it can be easily converted into the rutile phase upon heating, and the heating temperature is generally above 700 degrees Celsius. So, the correct option is option C, 700 to 800 degrees Celsius. Now, we will move on to the fourth question. The driving force for the anatase to rutile transition is option A, increase in Gibbs free energy, option B, decrease in Gibbs free energy, option C, decrease in enthalpy only, option D, increase in entropy. So, the main driving force for any structural transition is a lowering of the Gibbs free energy. Anatase is a metastable one and its Gibbs free energy is higher. So, it always have a tendency to move on to or to convert into a more stable one having a lesser Gibbs free energy. Lower the Gibbs free energy means greater will be the stability. So, here the correct option is option B, decrease in Gibbs free energy. The driving force for the anatase to rutile transition is a decrease in Gibbs free energy. Next question. When TiO2 particles are in the nanometer range, for example less than 40 nanometers, which phase becomes relatively more stable due to surface energy effects? Option A, rutile, option B, anatase, option C, brookite, option D, cotonite type TiO2. We have seen that among the three polymers of TiO2, rutile is the most stable phase. However, when the particle size is smaller, there will be surface energy effects which leads to stability. So, the anatase phase, which is generally metastable at normal conditions. So, when the particle size becomes very much smaller in the nanometer range, that is less than 40 nanometers, the anatase phase becomes more stable. So, the correct option is option B, anatase. Last question. The TiO2 polymorph having orthorhombic structure at ambient pressure is option A, rutile, option B, anatase, option C, brookite, and option D, TiO2 2. We have discussed about the three crystal structures of TiO2. Anatase and rutile these both have a tetragonal structure, one with a dense form. Rutile has a densely packed arrangement, whereas anatase has a more open arrangement. On the other hand, brookite have a orthorhombic structure. So, here the correct option is option C, brookite. So, brookite is a polymorph of titanium dioxide with orthorhombic structure. So, today we have discussed about the structural transitions in different polymorphic forms of titanium dioxide. Thank you.